Hello, allow me to present a summary of my work entitled, Experimental Approach for the Study of Wood Strength at Fracture in Mode 2 by using a modified prototype test specimen and confrontation of the results with those of the 4ENF test. Application, Eucalyptus Grandis. To do this we have adopted the following plan. We will start with, an introduction. And to situate ourselves we will explicit the different previous works through a state-of-the-art. To understand the behavior of the material we performed a mechanical and physical characterization of the Eucalyptus grandis. Then detail the method we adopted to determine the strength at Mode 2 fracture using an adopted specimen, and finally, a conclusion. Wood is a material very used for several centuries, as the Yingxian Pagoda in China testifies. Built in 1056, it reaches a height of more than 67 meters. This construction entirely out of wood could survive several wars, earthquakes or lightning. Wood is also used in the constructions which respects the environment, as is the case of the refuge of Chamonix in France, which is built on an altitude of 3,835 meters. This refuge could, thanks to its construction entirely out of wood, win several prizes. In fact, wood is a competitive material in construction for a number of reasons, including thin and light constructions with a high level of pre-finishing. Construction elements are almost entirely prefabricated, that allows us to get gain of time, and stability, lightness and fire resistance. But, these constructions can be subject to collapse, as the case of the Olympic swimming pool in Tangiers in 2016, and this is mainly due to the lack of knowledge of the behavior of a wooden structure subjected to external stresses that cause breaks by one of the known modes by Mode 1, Mode 2 or Mode 3 or Mode 1+2. Mode 1 has been widely studied until a standard test to determine the parameters G2C and K2C was carried out. Mode 2 is still subject to research. In order to understand and control the phenomena related to this mode of rupture, several prototypes have been developed, mainly ENF, ELS and 4ENF, but others have been designed and applied. Indeed, the Mode 2 stress intensity factor (KIIC) for balsa wood was measured by Wu using thin plates with a central crack, taking care to use specimens long enough to test the hypothesis of an infinite plate model. Kramer and Pugel used a compact shear specimen to characterize the Mode 2 toughness of southern pine. In the LT plane, we also find that Combs used the compact tension shear specimen designed by Richard for isotropic materials to estimate G2C. All these tests were well carried out, but several difficulties slow down a deeper investigation in these prototypes. One quotes among the observed obstacles, the experimental assemblies which check the purpose of the test are very difficult to carry out. Also, a bifurcation of the crack is in general observed from the beginning of the test. For this reason, only the three tests mentioned above will be considered in the following. We start with the first one used for the characterization of straight sliding failure Mode 2 of wood, namely end-notched flexure (ENF) by Barrett et al. In 1977. This test consists of subjecting a beam containing an artificial defect on one of its sides to a three-point bending test as shown in the figure. This test appears to be easy to apply, but it presents many difficulties when analyzing the results. Crack tracking is impossible without high-tech means, and crack propagation is unstable for values of a greater than 0.7 L. This presents an inconvenience related to the nature of the test. Several researchers have adopted this prototype in their studies. MFSF de Mora et al. Used this prototype to calculate the G2C using wood from the Pinus pinister. 24 specimens were machined and conditioned at 20 degrees Celsius and 65% relative humidity until equilibrium was reached, resulting in a moisture content of 12% in the wood. The average specific gravity was 0.55. The initial crack was introduced in two stages. Initially, a notch was machined with a band saw 1 mm to 2 mm thick. Then, the notch was extended using a cutting blade and taking care not to apply a large load during the operation. The initial length of the crack, which is a fundamental parameter, is said to be accurately measured. 2 sheets of Teflon film were inserted between the two surfaces of the initial notch in an attempt to minimize the effects of friction. The mechanical tests were performed in a universal screw testing machine Instron 1125. The specimen was supported by 2 cylinders and loaded at mid-span with a traverse speed of 5 mm per minute. The applied load and displacement values were recorded during the tests. To measure the length of the crack during propagation, a scale was marked on one of the edges of the specimen. However, it was quickly concluded that significant errors were made due to the uncertain identification of the crack bottom. In the figure, a discontinuity can be observed on the second black vertical reference line, detail 2. However, the position of the tip of the crack could not be defined because practically no change is evident in the second edge of the specimen. Furthermore, it cannot be ensured that this discontinuity on the black line corresponds to a continuity of crack propagation. Another interesting prototype is also called the end-loaded split else. This test is shown in figure. The sound side of a prismatic specimen is embedded while the side containing the artificial defect is loaded in the thickness direction. The loading is usually applied to the specimen through a loading block. The else test provides stable crack propagation in mode 2 if the condition A.L greater than 0.55 is satisfied. Nevertheless, it requires a rather complicated assembly to maintain the conditions of the sliding embedding. Several researchers have used this setup, including Mal Silva et al., who adopted this model to try to solve the problem of crack tip determination. In fact, Silva used 19 specimens of Pinus pinister wood with a moisture content of 12% and an average specific density equal to 0.57. The notch was introduced using the same method as MFS de Mora described above. Mechanical testing was performed in a universal screw testing machine Instron 1125. The ELSE testing machine included a linear guide system allowing horizontal movement of the collet translation during loading. The tests were carried out in a travel control mode with a crosshead speed of 5 mm per minute. 2 sheets of Teflon film were also inserted between the initial crack surfaces to minimize the effects of friction. During the tests, the applied load and displacement values were recorded. As with the ENF test, it is difficult to detect the crack tip figure. In the curve shown in the figure, it can be seen that the behavior of the wood during loading is brittle up to the maximum breaking load P critical. Another alternative, the latest 4-end notched flexure 4ENF specimen, a specimen containing an artificial defect on one of its sides is loaded in 4-point bending. This prototype has the advantage of being the most stable, but the friction effect is very apparent during handling. Disadvantages major of the 3 prototypes test 3ENF, ELSE and 4ENF. Extent of fracture surface. Appearance of mode 1 and 3. Difficulty of crack tip determination. Necessity of using sophisticated equipment. Necessity of using sophisticated equipment. To determine G2C we adopted this succession of steps. Step 1. Choice and characterization material. We have conducted a complete characterization of the wood considered, physical and mechanical. Step 2. Design and realization of a new prototype. Specimen geometry. Confection of test specimen. Conditioning of test pieces. Step 3. Study of the toughness in Mode 2 by carrying out tests and determination of G2. Step 4. Validation of the designed prototype. To do this, we analyzed SEM fractography and performed a comparison of the improved prototype with the 4ENF prototype. To better understand the material used, we will in this step explain the results of the characterization of the selected Eucalyptus grandis species. The specifications of this tree: the Eucalyptus grandis is leafy, growth wood fast. And 40 meters height. Area in Morocco, 4% of the Super-C total of eucalyptus. The forest of Rabat, Chemisit, Tetuan, Tanger and Ben Slimane. We use this tree in industrial production, pulp, firewood, poles, wood artwork. Examination of the experimental results shows that the density of Eucalyptus grandis varies between 0.5 and 0.58, taking into account the classification of the NFB 51005 standard, which allows us to conclude that Eucalyptus grandis is a light wood. If we examine the results obtained from shrinkage, we can see that Eucalyptus grandis is characterized by a volume shrinkage of 15.54%. Referring to the NFB 51006 standard, the value obtained from this shrinkage allows us to qualify it as a wood with high shrinkage. The mean, maximum, minimum, and standard deviations of the basic mechanical properties of Eucalyptus grandis wood, such as compressive strength sigma A, longitudinal Young's modulus, and flexural modulus of rupture by bending of the specimens studied, are grouped respectively on the second table. It is concluded that Eucalyptus grandis has very important mechanical characteristics which gives it a high rigidity. In order to analyze the fracture behavior of fibrous materials such as solid wood, it is important to determine the properties of the fracture mechanics such as the energy restitution rate and the stress intensity factor of the different fracture modes. The in-plane shear mode 2 is indeed one of the modes that cause the collapse of the wood structure. In what follows, we will explain the different stages of the tests carried out. In order to highlight the plane shear on a wooden specimen that we want to be easy to achieve and reproducible, we have consulted a series of publications dealing with this phenomenon, as well as the experimental devices developed in our laboratory. We have chosen a specimen inspired by the shear test according to the standard NFB 51012. After several attempts and by taking inspiration from the various devices, we were led to choose the geometry which according to our study will give better results. This one is presented in figure whose dimensional characteristics are shown in the table. During the test, part 1 slips with respect to part 2 under stress, which creates a plane shear. All the specimens were taken from logs of Eucalyptus grandis wood. The specimens are notched along the longitudinal direction in the TL plane, so that the rings are parallel in the TR plane. The speed of displacement of the crosshead selected for the test is 0.5 mm per minute. The test is stopped when a sudden drop in load is observed. The figures show typical load displacement curves of Eucalyptus grandis for notch lengths of 4 mm and 12 mm. The behavior of the specimens during the test can be described as elastic under the action of the applied load. It should be noted that the crack propagates almost linearly until the maximum load is attained. It should also be noted that all the curves recorded show irregularities during loading which can be attributed to several reasons such as wood heterogeneities, internal defects, variability in the growth rings and the sliding of the fibers between them. Cracks tend to propagate in the growth rings corresponding to early wood low intensity. To ensure the validity of our results and to take into account the known dispersion of the wood, the tests were carried out on a set of more than 50 specimens, taking care to divide them into 5 batches of specimens of notch length A equals 4, 6, 8, 10, 12 mm. The test is carried out in controlled displacement with a constant speed of 0.5 mm per minute. As previously stated, the average tensile load decreases as the length of the notch increases. The mean values of the critical G2 and the critical K2 are obtained using the Irwin-Keiss method, which is based on the determination of complacency. In the figures, a dispersion is observed for each value of A, except for the value of 12 mm. This dispersion is less visible. It is also noted that the crack propagation is stable from the ratio A/W equals 0.2, hence the stability of our prototype. We can conclude that for all values of the ratio greater than A/W equals 0.2, G2C and K2C are characteristics of the material. The Mode 2 fracture surface is characterized by severe torsion, tearing and unraveling of the trachid walls as can be seen in the figure. The results of the seeding studies allow the characterization of the Mode 2 fracture facies for this species. The figure shows the photomicrograph of the crack initiation for a notch length that equals 6 mm, where 2 zones can be seen for Eucalyptus grandis. Area A shows the tip of the notch machined by the jigsaw of the same thickness, while Area B shows the area in the breaking process. The Mode 2 fracture surface is characterized by a more severe torsion, tearing and unrolling of the tracheal walls. The loosening of the fibers is very apparent. In order to compare the results obtained using our specimen, we considered it important to carry out the most common test for the study of this mode of rupture for wood material. In this section we will explain the results of test 4ENF. The test is carried out in controlled movement with a constant speed of 0.2 mm per minute. The average load decreases as the length of the notch increases. The behavior of the specimens can be described as elastic under the action of the applied load. To guarantee the validity of our results and to take into account the known dispersion of the wood, the tests were carried out on a set of more than 70 specimens. These figures show the relationship between the parameters K2C and G2C and the crack length A. The analysis based on the fracture mechanics is essential even for small notch lengths. We also use the Irwin-Kaiss approach. We can see a dispersion of the results and an instability of the crack propagation. This is probably due to the extent of the propagation zone. To measure the length of the crack during propagation, a scale was marked on one of the edges of the sample as shown in the figure. However, we realized that errors can be made when identifying the bottom of the crack. In the figure, a discontinuity can be observed from the first black vertical reference line, detail 1. However, the position of the crack tip could not be defined, as it cannot be guaranteed that the discontinuities on the black lines correspond to a continuity of crack propagation. In this section, we are interested in comparing the results obtained from the test on designed specimens with those of the 4ENF test, which is considered the most reliable among the others but which also presents difficulties in data acquisition. The figures and present respectively a comparison between the energy restitution rate and the stress intensity factor obtained from the test on the study specimen as well as those of the 4ENF test for Eucalyptus grandis. The two figures show an acceptable agreement between the two tests. Conclusions. In this work we were able to carry out a mechanical and physical characterization of the studied species, we were able to improve an easy test for the study of the mode 2 of wood and finally to compare our results with those of the most used test for the study of this mode where a great concordance was found.